Hello everyone, I am Bob and this is the Home Bitcoin Immersion Mining channel. In this build series episode, we're going to cover the build of my dry cooler, including how I'm attempting to build a quiet, neighbor-friendly design. So with that, let's get started. Hey folks, before we begin, I want to know what you are building in your home Bitcoin immersion mining setup. Whether it's a carefully designed wonder of craftsmanship or something held together with duct tape and baling wire, I want to see it. And so does everyone else. After all, we are all learning how to figure this out, and the more we share, the more we can learn about how to do this better. So, send me photos of your setup along with your name, location, and whatever else you want to share about your build. Send your information to the email address shown below, and I'll be showing your home builds as part of future episodes so we all can see what can be done with home Bitcoin immersion mining setups. So with that, on with the episode. Okay, in the last episode, we covered all the different options for rejecting heat from miners, and that would include ground cooling, cooling towers, adiabatic coolers, air conditioners, and dry coolers. Now, I could walk through each of these options and talk about the upsides and downsides for each one for my home setup, but as was covered in that episode, the one option that makes the most sense for most home setups, including mine, is a dry cooler. So I'm just going to skip all the details and get right into my dry cooler design and build. Now, I could have bought a dry cooler made by a vendor of single loop systems. I also considered buying a couple hydraulic oil coolers, but instead I'm going to build my own because, as I noted way back in the first episode, I'm an engineer and I like building things. And I also want to try something a little different to see if it'll work here. Now, as I've noted before, for my mining system, I've got two SJ19 Pros generating a little over 6 kilowatts of power. In future episodes, I'm going to show how I'll be using all that energy to heat my water and heat my house, but like in all home designs, I don't always need hot water and I don't always need to heat my house. In fact, in my part of the country, it can get well over 100 degrees in the hot days of summer. So I need to design a dry cooler that can dissipate at least 6 kilowatts of power in over 100 degree heat to run my system year round. Now, way back in another early episode, I went over the layout of my system, and as I noted in the site walkthrough, my dry cooler is going to be located at the side of my house where I have neighbors close by. So I really want my dry cooler to be something that's not going to make a lot of noise. And with that in mind, my first step in building my dry cooler is to pick out my radiators. And I decided to go with an oversized design. So I picked out two radiators, each being about 2 foot square. Each of these radiators have 3 rows of copper pipes, increasing the heat transfer to the air passing through the radiator. And together, these will give me 8 square feet of radiators for 2 miners. I have the link below for the radiators I'm using if you're interested in getting something similar for your system. And the reason why I'm using these very large radiators is I'm going to orient these horizontally instead of vertically, as you'll see in most other home setups. My thinking here is that with this horizontal design, I should get some degree of thermal convective effect. The idea here is the radiators will heat up the air, causing it to rise, pulling in more air through the radiators to help cool them down even more without needing as much fan power to move the air. Now, it's really hard to calculate how effective this thermal convective effect will be, so I'm going to just give it a try and see how it'll work. I'm hoping this will be strong enough that for most times of the year, a fan will not be needed. But since I won't know how well this will work until it is up and running, I will be adding a fan that should be strong enough to dissipate the heat from my mining system. And when it comes to picking out that fan, I thought a bit about what type of fan I needed here. I needed a fan that could move 2500 to 3000 CFM. I needed a fan that could handle being exposed to hot temperatures, freezing temperatures, rain, snow, pretty much any type of weather. I needed a fan that is reliable and will last for a very long time, and I wanted something that would be relatively cheap. And so what I picked out is a 16-inch automotive radiator fan. Because when you think about it, these fans are made to operate under really tough conditions. They're under the hood of your car, they see hot temperatures, freezing temperatures, rain, snow, road salt, dust, dirt, and they are made to handle all of this for the life of your car. After all, when's the last time you've heard of someone complaining that their car fan failed? These things are usually made to be fairly bulletproof, so it seemed like the perfect option for my dry cooler setup. Now, car radiators can be a little noisy. Sometimes they are one of the biggest sources of engine noise. So I ordered a few different 3000 CFM fans from Amazon. I picked out the fan that I thought made the least amount of noise, and I have a link below for the one I selected if you're interested in buying something similar. Now, the downside of using an automotive fan is that these things are designed to be powered by your car's 12-volt power system, which provides a huge current supply for the fan to start up and run. So, to get the fan to operate, a decent sized power supply is needed. I have a link below for the power supply I'm using. It should be big enough to operate most any 12-volt automotive fan. So, with the radiators and fan selected, the next step was to put them all together. And this is pretty easy. I used 1-inch copper tubing to connect my supply lines to the radiators and to connect the radiators to each other. I'll be covering my supply lines and the entire cooling loop in the next couple episodes. Now, if you're new to copper pipe soldering, it's really not that hard to get halfway decent and to be able to make good joints. You need a good torch, some tinning flux, a soldering wire, and some practice. I've linked a video below that gives some good how-to information, and there's a ton of other good videos out there just like this one covering how to solder pipe correctly. And really, the key here is to get in a little practice before working on your system. My recommendation is to go and buy some cheaper 1/2 inch or 3/4 inch piping and fittings and make a few practice joints, get comfortable with wielding a torch, and then move on to working on your system. And so with my basic design covered, let's go see how it turned out. Hey folks, just a quick reminder to hit that like button so the YouTube algorithm will share all this good content with other people, and for you to hit the subscribe button so you won't miss any good content coming your way. With that, back to the episode. Okay, so I'm going to stay behind the camera here because it's just going to be easier to shoot the video this way. Now, as you can see, I've got my radiators mounted to the side of my house using 1 1/2 inch angle iron. This material is fairly cheap and you can find it readily available from your local home improvement store. Now, the empty radiators aren't that heavy, but when they are full of coolant, they can weigh quite a bit, so I've anchored everything into the wall studs to support the weight. As you can see, the dry cooler is mounted high up on my house, and this is because it matches the height of the cooling lines as they are routed through my garage. This also gives me some room underneath the dry cooler for a future storage shed I've got planned for this area. Now I've got plenty of clearance around the radiators for hot air flow, and they are mounted horizontally to hopefully use natural convection to minimize the need for a fan. But one of the downsides of mounting these horizontally is the radiators can catch leaves and other debris that can impede airflow. There is a tree nearby, but it really doesn't grow a lot of leaves, so I might have to clean things off once a year or so, but if the horizontal mounting helps me with convective cooling and makes it for a quieter design, I think it's worth the hassle. Now, another problem with horizontal orientation is that this can absorb a lot of heat from the sun beating down on it all day, hurting the cooling efficiency. But for my setup, this really isn't going to be a problem. This location is at the northeast corner of my house, and for most of the day, year-round, this is in the shade. So solar heating really shouldn't be a problem for me. Now up on a ladder, here's my pipe routing and fan mounting. The pipe is routed to put the radiators in series, with the idea being the first radiator will have the strongest convective effect, hopefully transferring much of the heat into the air without the help of a fan. The second radiator will finish the job, with the fan helping out when needed. For both radiators, I have the hot coolant flow entering the top and exiting the bottom of the radiator. This puts both radiators in a counterflow configuration. This is the most effective way to get heat transferred from the cooling fluid into the air. As you can see, the fan is mounted to the radiator using the zip lines that came with the fan, and the fan is oriented to pull air up through the radiator, aligned with the natural convection direction. Now, before I step down off the ladder, a couple more details. I've covered the 12-volt wires for the fan with UV-rated heat shrink wrap to protect them from the weather. Even though there's not a lot of sunlight here, over time, UV light can really damage things, so I figured it was worth the extra work to add some protection here. Also, I haven't applied sealing to the piping passing through the wall yet. I'm going to do that later after I finish leak checking the entire system. Now, in the last episode, I covered a couple tricks to protecting your miners through the cold winters, and I'm going to be using both of those here. First, when it comes to controlling my fan, I've got a temperature switch built into the outlet of my radiators. I'm using the same Whitman Controls temperature switch I used in my miner cooling loop, and I've covered this in previous episodes, and I have a link below if you're interested in using something similar for your setup. Now, when it comes to controlling the fan with the temperature switch, my design was kind of pieced together, and it really isn't that great. An automotive fan pulls a ton of current when it starts up, so using the temperature switch to turn the power to the fan on and off won't work. It'll overload the switch and burn it out. So I decided to use a definite purpose contactor relay to control the power to the fans and have the temperature switch control this relay. I bought the relay from C3 Controls. As I noted in a previous episode, their prices are really reasonable and they have many different options and types of sizes of components. I have a link below if you're interested in buying something similar. However, when I bought the relay, I made the mistake of buying a 24 volt instead of 12 volt model, so now I have a control circuit with two different DC voltages. 24 volts for the control relay and 12 volts for the fan. Looking back, I should have just bought a large 12 volt power supply and kept everything run on 12 volts, but hindsight's 2020. So with that, here's my circuit design. I have a 12 volt power supply which powers the definite purpose contactor relay, and I have a 12 volt power supply which powers the fan. When the temperature of the fluid exiting the radiators exceeds the temperature threshold of the switch, which in my case is 100 degrees Fahrenheit, the switch will close. This will activate the relay, which will send power to the fan. The fan will then continue to run as long as the temperature of the fluid exiting the radiator is higher than 100 degrees Fahrenheit. Now I also added a single LED to the circuit that will tell me when the fan should be running. This really isn't needed, but I'll be able to tell when the fan should be running and if there's a problem. So with that covered, here's a photo of how it turned out. As you can see, I put everything in an electrical enclosure that I had left over from a previous project, and this will keep everything neat and contained. Here is the 12 volt and 24 volt power supplies, and here is the definite purpose contactor. I have links for all of these things below if you're interested in getting something similar. Now, my wiring here isn't as nice and neat as that in my control box, but it'll work and keep everything from shorting out. I've got a 120 volt power cord running into the box to power both power supplies, and I've got the wiring input from the temperature switch and the wiring output to the fan coming out the bottom of the box. Now I've tested the design by shorting across the temperature switch, and the relay closes and the fan turns on as designed. So although this looks a little rough, it will work great. Now if I was to redesign the system, I'd make this a lot simpler. I'd buy everything to run on 12 volts and just use a single power supply. Here's the simplified circuit design I'd use in that case, and as always, I'm not an electrical engineer, but maybe this would give you some ideas for building your system. Now in the last episode, I also talked about using a thermostatic mixing valve to control miner cooling, and I'm going to use this trick in my design too. Now, I didn't do anything special here. My design follows exactly what I covered in the last episode. So if you want more information, you know where to look. When picking up my valve, I tried to find the best compromise between fluid flow and price. I ended up buying model LFLM490-10 thermostatic mixing valve made by Powers. I have the link below if you're interested in getting something similar. And with that, here's a photo of my radiator piping. Now, looking at this image, there's a bunch of other components here. We have air vents, valves, pressure, and temperature gauges. These really don't affect the cooling design, and I'll cover these in the next two episodes covering hydronic system design. But focusing on the basic plumbing, here's the pipe carrying the hot fluid from my miner, sending it to my radiators. And coming back in from the radiators, the cold coolant is directed into the mixing valve. And as I covered in the last episode, the mixing valve will control the temperature of the fluid returning to my miners. Okay, so that's all I have for today. My dry cooler is built, my coolant lines are connected, and my fan is hooked up and ready to go. So next time, we're going to cover the basics of hydronic systems and the design of the secondary cooling loop for a home Bitcoin immersion mining system. So with that, bye.